In this video, we will solve the exam of January 2020 with the exception of the sub-questions that are related to theory because they are covered by the overall video course. Well, the first question is as follows. Give the definition of the four fundamental subspaces and find bases and dimensions for all fundamental subspaces of the matrix that is shown. Well, what is the rank of the matrix, and then express the last column of the matrix in terms of the other columns. This question will not be treated in this video, as you can find it in video 7, where it is the first whiteboard exercise. So here's the second question. Find the values of a and b for which the system of equations ax is equal to b, a is given here and b is given here, has no solutions, an infinite number of solutions, or a unique solution. For the values of a and b for which there are an infinite number of solutions, express this solution in full detail. So first try to do this exercise by yourself and push the pause button. Well, as usual for this type of exercise, we have to create the augmented system and then apply Gauss elimination. So we create zeros below the pivots, right? At the start, not above the pivot. So we bring it in echelon form, upper triangular form, and then we can start the discussion. So let us do this. We have a pivot over here and we have to create zeros below the pivot. So we use the following elementary operations, and you can see that the multipliers are a and 1, the element to eliminate over the pivot. If you do the calculations, this is what you obtain. We have a pivot over here and we want to create a zero below, and as you can see, we have to do the following elementary operation with a multiplier -1. If you go through the calculations, this is what you obtain. So now we'll start the discussion, and we'll start the discussion with b different from 1, right? Well, you can see that if you have b different from 1, right, this will be non-zero, and you have this one 0, well, then you have a problem and there are no solutions, right? So this one is 0 for a is equal to 1 and a is equal to -2. So b different from 1, a equal to 1, no solution, and b different from 1 and a is equal to -2, no solutions. If b is equal to 1, we have a 0. Well, this is nothing special except if this one is 0 here, because then we have an infinite number of solutions. So if b is equal to 1 and a is equal to 1, we have an infinite number of solutions. And if b is equal to 1 and a is equal to -2, we have an infinite number of solutions. Well, we have to treat the case where b is equal to 0 separately, because then we have, well, a 0 appearing over here and we obtain this situation over here, right? You can see that when a is equal to -1, here we have a line of zeros appearing, and this will also lead to an infinite number of solutions. But you can see that when a is different from -1 and b is equal to 0, of course, then we have here equations, the second equation and the third equation, that are not compatible, right? So in these cases we have no solutions. All other cases will lead to a unique solution. So what we have to do right now is, for these 3 cases that correspond to cases of a and b where we have an infinite number of solutions, we have to express the solution in full detail. So what we'll do, we'll start from this one and we'll plug in the values of A and B in these three cases. What we'll do is treat the three cases that lead to an infinite number of solutions, and we'll start from our augmented system in echelon form. So these are the three cases that we have to treat, and we'll start with A is equal to 1 and B is equal to 1. And if you inject the values of A and B, this is what you obtain. The particular solution can be read over here. And now we have to find the two solutions that correspond to the null space of A, and therefore we have to construct this matrix over here. And if we look at that, this is really minus 1, minus 1, and we put an identity matrix below, right? And well, the base of the null space is constructed from these two solutions over here, and if you take a linear combination, well, you obtain a solution of the system of equation in this particular case. So let us now go to this case over here. When we inject the values of A and B, we have here indeed still our system in echelon form, and what we want to do is create a 0 over here and a pivot of 1 over here, so that we have the row reduced echelon form. And therefore we have to do this row elimination, yes, and multiply the pivot by a third. And if you do this, this is what you obtain. Here again you have the F, so the particular solution can be read over here. If you construct F, this is what you obtain. So the total solution is the particular solution plus alpha times the solution that comes from the null space of A, right? And then we have to look at this case here. B is equal to 0, A is equal to minus 1. This is what you obtain. So what you could do is start to exchange columns and rows to bring it in a form that would look like this, but this would be too much work, so there is another way to do it. Here we simply look at the third equation, so 2x3 is equal to minus 1, so x3 is minus a half. Once you have x3, the first equation tells you that x1 is a half, and as you can see in this system of equation, well, x2 can be any real number alpha. So we can write the solution as follows. Well, here is the third question. It's about least squares and the QR decomposition. The question is, well, find the circle, and the equation of the circle is given, that best fits the data, and you receive n data points, and you have to write this problem in the form of a least squares problem. Then you have to solve the problem in a particular case where n is equal to 4 and you're given, well, 4 points. And well, to help you, if you have not been able to solve the first part of the question, we tell you that, well, this leads to a least squares problem. Ax is equal to b, with a given over here and b is given over here, and you have to solve this problem using the QR decomposition. So once you have done this problem, right, well, you have to see that if you particularize it to this case, well, you obtain indeed a problem Ax is equal to b, that is this one over here. As usual, try to do this exercise by yourself and push the pause button. So let us look at the first part of the question. What we have to do is write that every point here, and there are n, is on the circle. Of course, since there are more points than there are unknowns, that will be impossible, and this will lead to a least squares problem. So imposing that xi, yi is on the circle leads to this constraint, and we'll have this constraint for I is equal to 1 up to n. If we expand this, this is what you obtain. And what we do here, since xi and yi are known, is put everything that is known on one side and, well, everything that has something that is unknown on the other side, right? The unknowns here are xc, yc, and r. So here you have xc, will take this one as x1. Here you have yc, we'll treat this one as x2. And here, well, you have something that is dependent on the squares of the unknowns. So we'll set this one to x3. The idea is that if you have found x1, x2, and x3, well, you'll be able to compute r, right? So if you put the unknowns in a vector, x1, x2, x3, you can rewrite this equation as follows. And here on the right side we put what is known, again because xi and yi are given, right? So here we have given or written the equation for one I, but we have to do this for I ranging from 1 to n, and this will lead to the following least squares problem. Okay, you can see that they are all lines of this type where I is ranging from 1 to n. And we have here a least squares problem where A has 3 columns because there are 3 unknowns, and there are n rows because we have, well, to fit the n points here to the circle. Now we can have a look if this is okay if we have n is equal to 4 with this input data. So let us look at the first row over here. So we have to take 2x1, x1 is 3, so this is 6, to y1, y1 is 0, so this is a 0. We have the 1 over here, and here we have x1 square, so that's 9, plus y1 square, that's 0, so that's a 9. If you check this for the other rows, you will see that this is indeed the least squares problem we end up with in this particular case. Well, let us now turn to the second part of the question. We have to solve ax is equal to b, which is a least squares problem, using the QR decomposition. So we have to find the QR decomposition of the matrix A. As usual, we keep the first column of A. This is what you have over here. And then for the next vector, we have to take the second column and, well, remove the projection of A2 on A1 bar, right? Well, if you compute this projection, this is what you obtain. You can see here that A1 bar scalar product with A2 is 0 because, well, these two columns are already perpendicular. So A2 bar will also simply be A2. As usual, you should always check when you obtain the vectors that they are indeed perpendicular, and this is the case. Then next, A3 bar, well, you take the third column, you withdraw the projection of A3 on A1 bar and the projection of A3 on A2 bar. This one will give 0 as well because A1 bar and A3 are perpendicular. As you can see, this is A1 bar, this is A3. If you take the scalar product, this is 0, and you'll have a contribution from this term over here. The scalar product of A2 bar and A3, well, that's a 6. And if you take the scalar product of A2 bar by itself, we have a 20. So that's 3 over 10, right? And you end up with this expression over here. If you go through the calculations, this is what you obtain. Of course, we are interested in these vectors, but we have to give them a unit length, and this leads to Q1, Q2, and Q3, right? So this is how we obtain the matrix Q. We know that A is equal to QR. If we pre-multiply this equation by Q transpose and use the fact that Q here is an orthogonal matrix, well, we obtain that R is equal to Q transpose A. By the way, of course, here again we should, well, probably easier over here, we should check that this one is perpendicular to this one and perpendicular to this one, and if you look at this, and you will see that this is indeed the case. So R is Q transpose A, this is Q transpose, right, and this is A, and if you go through the calculations, this is the R that you obtain. And remember, check that these elements are indeed 0, right? So we have R here, we have our original problem, AX is equal to B, A is QR, so QRX is equal to B. We pre-multiply by Q transpose, and this is what you obtain. So R, this is R, X, right, is Q transpose, and this is B. If you go through the calculation, this is what you obtain, right? And you have here a system Rx is equal to this, and it's in upper triangular form. So what you can do is use back substitution. As you can see here, well, 8 is the value of x3, so that's correct. From the first equation, well, you have a 0 over here, you see that x1 is equal to 0, and if you inject x3 in the second equation, you can see that x2 is minus 3/2. So this is x1, and this was xc, and this is yc, x2. We still need the radius. Well, this is x3, right, which is equal to 8, but x3 was r squared minus x1 squared minus x2 squared. We have x1, we have x2, so we can obtain the value of r squared and also the value of r. So here is question 4. Find the values of A for which the matrix that is shown is positive definite. For a value of A of your choice, of course that makes the matrix positive definite, compute the two factorizations R transpose R of the matrix A, the one related to the pivots and the one related to the eigenvalues. As usual, try to do this by yourself and push the pause button. So let us have a look at the values for which this matrix is positive definite. Here we'll use the upper determinants to see or to impose that this matrix is positive definite. We could have used another method, for instance, well, we could have applied Gauss elimination to this one and computed the pivots and imposed that the pivots were positive, right? So we'll use this method of the determinants, the upper determinants. So this one, that's trivial, that's a 2. This determinant over here, that's 3, that's positive. So we have to impose that this determinant is positive, and we construct the determinant over the first line. And if you do, this is what you obtain. If you do the calculations, you obtain a second order polynomial that has to be positive, right? You can compute the roots. The roots are -2 and 1, and as you can see here, because of the minus sign, for large values of A, this will be negative, right? So we'll have positivity between the roots. You cannot take 1 or -2 because this would lead to, well, matrices that are positive semi-definite. So there are two obvious choices. A is equal to 0 and A is equal to -1. So here we look for the factorization R transpose R of the matrix A related to the pivots. Over here you have the matrix A for A is equal to 0, and here for A is equal to -1. And what we have to do is, well, do Gauss elimination. So here we have a pivot, we need to create a 0, and we go further and we obtain the matrix U, right? To construct the matrix L, what you have to do is take the multipliers and, well, place them at the right spot in an identity matrix. So this one has been used to create a 0 over here, so you place it over here, and this one here has been used to create a 0 over here, so you have to place it here. So what you should do is compute L times U, and you should obtain A. By the way, the determinant of A is the product of the pivots, right? So we'll have 4 over here. So if we plug 0 in here, we have 4 as well. So this seems to be correct as far as the determinant of A is concerned. So we have an LU decomposition, but since the matrix is symmetric, what we can do is obtain an LDL transpose decomposition, where D is diagonal with the pivots on the diagonal, and you can use this to obtain your, well, R transpose R factorization of A. You simply take the square root of D, so this is this diagonal matrix with the square root of the pivots on the diagonal, and you multiply by L transpose. And by the way, since the pivots are positive, you can really do this operation over here. Here you have the calculation for A is equal to -1. It is very similar, and well, this is what you obtain. Again, here you can check that the determinant of A for A is equal to -1 is also 4, and indeed if you plug in here and here A is equal to -1, you obtain 4. So I have not done the calculations, right? But this is not that difficult. If you do not have time for this at the time of the exam, this is not that important. We'll now look for the second factorization, R transpose R, the one associated to the eigenvalues. We'll do this for A is equal to 0 and A is equal to -1. Of course, at the time of the exam, and this is also true for the other factorization, the one associated with pivots, you only have to consider one case, because it says for a value of A of your choice. And well, if you have the choice between A is equal to 0 and A is equal to -1, well, you can kind of see that A is equal to 0 is going to lead to a matrix with, well, more 0 elements, and at least for the factorization linked to the pivots, this is going to be easier, right? But in any case, you have to do only one. So here for A is equal to 0, since we have the factorization now related to the eigenvalues, we need to compute the eigenvalues, and you do this by obtaining the characteristic polynomial. This is the determinant of A minus lambda I. If you do the computation and you look for the roots, you'll find eigenvalues in 2, 2 plus square root of 2, and 2 minus the square root of 2. You remember that if lambda 1 is an eigenvalue, you can find an eigenvector by imposing that A v1 is lambda 1 v1, and this is indeed what we are doing over here. We have this system of equation that has to be 0. If you plug in the values of lambda 1, lambda 2, and lambda 3, these are the systems of equations that you obtain, and they allow you to find v1, v2, v3. So for instance, over here, it's obvious from the first and third equation that v12 is 0, and from the second equation that v11 and v13 are equal. So for instance, here what we do is impose v22 to square root of 2. From the first equation we have a -1 for v21, and from the third equation we'll have v23 is equal to 1, and then you have something similar for v3, right? Of course, we're looking for a factorization q lambda q transpose. Q here is an orthogonal matrix. Here we have vectors that should be perpendicular. You should check that. Here this is indeed the case, but they have not unit length. So you should ensure that they have unit length, and this is the case for q1, q2, q3. If you stack q1, q2, q3 next to one another, you obtain the matrix Q, and lambda is simply a diagonal matrix with the eigenvalues on the diagonal. A is Q lambda Q transpose, and we want to write this as R transpose R. So R is really the square root of lambda times Q transpose. So square root of lambda is just a notation for this diagonal matrix, right? Where we have, well, taken the square roots on the diagonal, and you can do this because the eigenvalues are positive. Since for A is equal to 0, we have shown that the matrix is positive definite. So here we have done this for A is equal to 0. I'll leave you the calculations for A is equal to -1, but here are the results. Well, there are eigenvalues in 1 and 4. There is a double eigenvalue in 1. So you have to pay attention if you do the exercise that you find two eigenvectors that are perpendicular, right? And then of course you have to give them a unit length. Notice here that they are perpendicular, right? And this is the Q3 associated to this eigenvalue lambda 3.